Good afternoon. So we will start today chapter 7, which is a chapter on probability theory. So we're going to learn a couple of interesting things about some basic things and some interesting things, hopefully, about the study of probabilities. So the chapter 7 is dedicated to probabilities. And I hope you will like it in the sense that knowing some basic things about probability theory is very useful in life. In particular, what I enjoy personally is the ability to actually figure out some of the things that may happen in real life in terms of estimating the odds of a random event in situations in which it's not maybe intuitive. Now, some people have a good intuition of probability even if they don't study it. But in many cases, sometimes the human intuition actually plays a trick on us, and mathematics is a nice tool to actually figure out the real answer in some situations. A typical example, for instance, which maybe you have heard about it, right? I mean, let's say you play at the casino and then, or let's actually make it even easier. You play a game of luck in which you get a prize if you flip a coin and you end up with the heads, right? So flipping a coin is a random event. The outcome could be either heads or tails. Okay, so someone, like I said, let's say heads is the winning outcome. And someone before you played this game like 5 times and ended up tails. So the person played the game 5 times, it lost 5 times, and then it, because it landed up tails 5 times in a row. So then the question is, when it's your turn, are you really, really, really confident that it's a huge chance or higher chance for you to actually obtain heads if you flip the coin, or it's still a 50-50? Now that's an easy question. If you don't if you don't figure out the right answer, don't feel bad about it, but it's still 50-50, right? Because the previous events that happened to the coin, however unlikely, won't affect the probability of the heads being 50%. So we're going to talk about stuff like that when we learn things like conditional probability. But in real life, some of these cases are not that easy to understand, or not that easy to have an intuition on, because in our minds sometimes we ask or we pose the wrong question from a mathematical perspective. So the probability theory will help us to rigorously define what we mean by a random event, what we mean by a space of probability, and then how you can answer rigorously mathematically what is the probability of a certain event to happen. So first thing first, in the first part of this chapter, we're going to talk about sets. Very basic stuff. Some of you might have already a knowledge about it, but we'll go through it just to make sure we are on the same page. And in particular, be very careful to make sure you understand all the notations and the operations on sets, because sets will be basically the main ingredient when we move on to defining what a probability space is and any other related stuff with probability theory. And by the way, a set in the mathematical sense, it's not really there's no real definition of a set, more like a description. So by a set we mean a well-defined collection of distinct objects. So anything that so a collection of distinct objects, well defined in the sense that there has to be some sort of a description of these elements. So they have to have something in common in terms of how you describe them. Now, sets can be very general. In fact, and let's actually mention it here because it might be useful for later, we can also talk about the universal set. That's a concept sometimes useful in mathematics, which is typically denoted by U. And this is basically the set with all possible objects. Okay, so any set basically, so any other set is a subset of U. So it's the set of all sets, in other words. The usefulness of this concept of a universal set is because often you may want to refer in a rigorous way to the stuff not in a set. So for example, if you have a certain set, then if you want to refer to elements that are not in that set, then that means they are in the universal set except the set you start with. That's not that important at this point, but I just wanted to mention that this description, this well-defined collection of distinct objects can be many things, including everything under the sun, right? I mean, everything in the universe. More down to earth, so to speak, typical sets, like I said, have some sort of a description of elements. So for example, you could have a set of digits. And by the way, before I actually mention these names, with these examples, let's actually establish already a notation for a set. So a set is denoted, or is this, yeah, it's denoted by capital letters, typically. You know, A, B, C, and so on. And its elements are either written between braces, right? So a typical set is described by the elements between two braces like that, or by a description of a typical element in the set, like the generic element if you want. So let's actually go over a couple of examples to make sure we understand what we're talking about. So for instance, you could talk about the set of all digits. So that means if you denote it by A, you can describe, or you can write this set by simply enumerating or by simply writing down the elements in that set, in this case the digits. Or you could have the set of all even digits, and that'll be 0, 2, 4, 6, and 8. If there are far too many elements, you could also describe the set, like I said, by a typical description of the element. It's fine sometimes to just write like this, for instance, C all digits, if we don't want to write all of them, if it's easy to visualize what they represent. This might be less common, because typically you either write all the elements like this, or like I said, you can have a more formal notation for the description of an element. So another alternative for A is to write A equals, and that's actually a typical notation in math. Make sure you get used to it once we go over a couple of examples. You can denote the generic element by a variable, let's say X, a vertical bar, and after that a description of what X is. X is a digit. So that's another way of writing down this set of digits. This vertical bar, you can read it such as, and again, you can use any letter, right? I mean, but anytime you can refer to the elements in the set by a generic description of one element, you could also write it down like this. So here's where it's useful. So let's say you have a set D that you want to say it contains all numbers up to 1000. So all natural numbers. So you could say D equals all the elements X such that X is natural number between 0 and 1000, right? So that's pretty much the only efficient way of describing the set without, in fact, writing down 1000 numbers, right, from 0 to 1000. Here's another example, referring back to the flip of a coin, the outcomes of a coin flip. That can be written in terms of a set, let's call it E. And because the outcomes are either heads and tails, you can describe the elements by the first letter of these words. There are no strict rules, by the way, on how to do this, right? I mean, people sometimes can write, for instance, 0, 1, and they associate 0 with heads, 1 with tails. I mean, the important thing is that the outcome of a coin flip, or toss, I think it's the correct term, coin toss. It's just 2 elements, right, distinct from each other. All right, so once we get used to the notation of a set, we're going to talk about some operations with sets. We're going to do that on the next page. And then a couple of examples, obviously, as we move along. All right, so one thing to establish is when 2 sets are equal. So 2 sets are equal when they have the same elements. I mean, that's pretty much obvious, right? And not just the same number of elements, right? So for example, if I have a set of digits, let's say 1 and 2, and B, the set of outcomes of actually, let's say B. Well, yeah, I mean, in this case, we denote the elements by H and T, so obviously A is not the same as B. But, you know, even if they have, let's say, 1 element in common, as long as they don't have the same number of elements, that still means that A is not equal to B. So they have to have the same number, I mean, the same elements. Obviously the same number, but identical elements. Another important notation or definition, if you want, at the same time, is the notion of a subset. So let's write it as a definition. We say that A is a subset of B if all elements of A are also elements of B, and not the other way around, right? So we denote this by A included into B. Sorry about that, I didn't meant to put a parenthesis here. So you read this A included in B. This notation here, it's like similar to less than or equal to, because if the sets are identical, you can also think about that the set is included in itself. So for example, A included in A, that's going to be true in a mathematical sense. And so here are a couple of examples. Suppose A is equal to 2, 4, 5, and B is equal to 1, 2, 3, 4, 5, and 6. Obviously, A is included in B because all elements in A are also elements of B, 2, 4, 5. But obviously, B is not included in A. For example, 6, 3, 1 are not in A. That will be very important later, so we know whether the two sets, one set is a part of the other when we deal with counting the outcomes of a random event and so on. Here's another important, let's see, yeah, another important definition. I mean, not so much of a definition, but a way of describing how these elements, how these sets look like in comparison to each other. Let's say that A and B don't have any element in common. then in that case they are called disjoint sets. So for example, if A is equal to 1, 2, 5, B is equal to 3 and 6, A and B are disjoint. Let's see. We're going to talk about the universe. Well, we'll talk about the complement later. See, when I mentioned before the notion of a universal set, that's also in the context of the problem. So for example, let's say, yeah, I mean, let's talk about in more detail this concept here because it will come up later. It's going to be important for later. So suppose you have a problem in which you only deal with digits. So, you know, in some sort of experiment, basically you work only with digits. So, I mean, if the problem is restricted only to these elements, you can think of the universal set as being these elements only. Right? Remember, without any other qualification, the universal set is the set of all sets or all elements possible in the universe. But if in the context of our problem, we only deal with digits for one reason or another, and we have basically dealing with sets of digits of various kinds, but basically we only work with these elements, it's fine to take the universal set to be just these digits. Now, why that's important? Because we have what is called, and let's write it down, the complement of a set. Which is basically, means all elements not in A. Okay, every element not in A. But where are those elements coming from, those that are not in A? Well, that depends, like I said, on the context of the problem. If you only work with the digits, then all the digits not in A. So for example, let's say A is equal to 2, 4, 5, 7, 9. Then the complement of A, there are various notations of this, by the way. Some, for example, this is denoted by A bar on the top, or A with a little letter C, you know, but typically with a bar on the top. So A complement means all the elements not in A, but also digits, right? Because these, like I said, we imagine we work only with digits in this problem. So you look at the universal set, in this case, all digits, and all the elements not in A are 0, 1, 3, 6, and 8. On the other hand, let's say for one reason or another, you work with all the numbers up to, I don't want to write too much stuff here. Let's say all the numbers up to 15. Then for the exactly the same set, the complement in that case, right, if you take the universal set to be all the numbers up to 15, well, of course, are all the elements not in A, but in this universal set. So that means 0, 1, 3, 6, 8, 10, 11, 12, 13, 14, 15. So whenever someone is asking you what is the complement of a set, one needs, or the problem needs to establish clearly what is that universal set, basically. We are working with digits, numbers up to 20, whatever the case is. Lots of little definitions here before we move on to more interesting stuff later. Also, for mathematical purposes and many other important purposes, we also have the notation of the so-called empty set, which is denoted by 0 with a cross across 0. The empty set is the set with no elements. And by the way, because of that, basically assume that the empty set is a subset of any set. That's also another useful concept to have for later. And then finally, before we close the lesson on this introductory part, let's talk about what we mean by union and intersection of two sets. These are two important operations that are very, very useful and widely used in the probability theory, as you'll see later. So let's do that on the next page. All right, so the intersection, excuse me, let's start with the union actually. So the union of two sets, A and B, is the set containing the elements from A and B, taken only once. Remember, each set is a collection of distinct objects. The notation for this operation is A with letter U and B. So the U in this context represents the union of two sets. So as an example, suppose A is equal to 1, 3, 4, 6, and B is 2, 3, 5, 6, 7. Then A union B, all the elements from A and B taken together. Just to write it down nicely, we can write it again in the increasing order. So this will be 1, 2, 3, 4, 5, 6, and 7. So notice that the possible common elements, which in this case are 3 and 6, are taken obviously only once in the union. So A union B, all the elements from A to B taken only once, obviously. That's implicitly understood because each set is a collection of distinct objects. That's an important part of the definition. So that is the union of two sets. The intersection of two sets A and B is the set containing the elements that belong to both A and B. Using the same example here, and by the way, the notation for this operation is A intersection B. So in this context, this symbol is the intersection of two sets. So like I said, for the same example over here, A intersection B will be the set made of 3 and 6, right? So the common elements. Sometimes, we're not going to do that too often, but in the beginning when people learn sets for the first time, it's useful to actually visualize the sets as partially overlapping diagrams like this. So A contains, and then put the common part in the overlapping portion of the two diagrams. So 3 and 6, 1 and 4, and then B obviously is 3 and 6 as well, 2, 5, and 7. So A intersection B is the common part in this type of notation. This is very important. You'll see when we talk about counting the elements in a set in the next section. But for now, this is the introductory stuff. Now, remember, if the two sets are disjoint, now we can actually write it nicely in terms of this notation we have with the intersection in the empty set. So for example, if A is equal to 1, 2, 3, B is equal to 5, 6, 5, and 6. A union B is equal to 1, 2, 3, 5, and 6. A intersection B is the empty set. No common element. And therefore A and B are disjoint in this case. So this is the basic stuff on the sets. Make sure you understand what a set is, what is the notation, how we describe the elements, basic operations, what disjoint sets are, what is the union, what is the intersection. And with that in mind, we're going to move on to another section pretty soon, when we actually deal with counting the number of elements in a set, which brings us much closer to the probability theory, because it's all about counting the possibilities and estimating the odds, right? The probability of an event. And to do that in more interesting applications, we need to learn essentially how to count elements in various contexts. So that's it for this lesson.